There we go. Okay, questions on the homework? What homework do we have today? 4.4 and 4.5? Yeah, because we didn't finish 4.6. So 4.4. Questions on 4.4?
Number 20.
What did that say?
In any vector space set that contains the zero vector must be linearly independent. Explain why.
So V is a vector space. Then any subset of V that contains the zero vector must be dependent. Is that what it said?
Yep.
Why? Okay, why is that?
Because the zero vector can be expressed as a linear combination of any set of vectors.
Exactly. So if we say S is V1, V2, to some Vn, and also a zero vector, then if we take something like 0 times V1 plus 0 times V2 plus we take a 1 times the zero vector, we get 0. So we have a non-trivial solution. Right, so 0 we can write as a linear combination of everyone else where their coefficients are just zeros. So, good. Other questions? In 4.4?
Yeah.
30? What does that say?
Let T sub A be equal Rn to Rn, not from Rn to Rn. Be multiplication by an invertible matrix A.
Okay.
And let the set U1 to Un be a basis for Rn.
U1 to Un is a basis for Rn. Okay.
Prove that T sub A in parentheses U1, comma T sub A of U2, all the way to T sub A of Un is also the basis for Rn.
Okay. What did you try here? So call this U. Assume U is a basis. Then what does this mean for U to be a basis?
It spans Rn.
U spans Rn.
And it's linearly independent.
Spans Rn means?
All linear combinations of it form the vector space.
Not exactly. Spans mean?
Any vector in Rn can be expressed as a linear combination of.
Right, so x is equal to C1 U1 all the way up to Cn Un, where x is in R, any vector in R. And okay, 2, we know that U is, what does that mean? linearly independent set is a linearly independent set, which means that C1U1 plus all the way up to CNUN equals 0 means that C1 all the way up to Cn equals 0. Okay, so those are the facts that we know so far. How do we get to this is also a basis? So note, here they defined our function for us. It's really multiplication by a matrix, right? So this would mean, for example, that TA of ui is equal to just multiplication by a of ui. Right? So we know that that's how we're defining this function. So what does that mean? How do I use that to get to proving this is a basis?
TA x and TA C1U1 plus CNUN is TA 0. So the second linearly independent one, we apply TA to both sides.
Are you doing?
Yeah, the second.
Oh, you're using two. Okay, so so first we show TAU1, however, is linearly independent. Okay, so now what were you saying?
TA C1U1. I mean the total, the left side of the equation, you can apply TA. It means you're gonna multiply by a matrix A with the total. It's TA 0.
TA is 0 vector.
Yeah, the left side is A C1U1 plus CN UN.
Right, so TA just means multiplication by a matrix, which by the properties of matrices, we can actually factor out constants.
Yeah.
So this is C1 times TA of U1 plus Cn times TA of Un equals,
0.
you get 0. Whereas when we're in Rn, so our 0 matrix is just a matrix with all 0, so that's going to be 0. And notice that we have C1 to Cn must be 0. This means, let's call this something, I don't know, BT. T is linearly independent. Okay, how do we prove that TA would span?
Let's take a vector in Rn. V can be expressed as linear combination of
You called it V?
x. Yeah.
V or X, whatever. Let V be in Rn. Then?
Then V is C1U1 plus C2U2 plus CNUN. If you apply that TA, you multiply both sides by A matrix.
Okay.
AV is A times the rest.
TAU1 all the way up to CN TAUN.
The left side is AV and A is invertible.
Right, equals blah blah blah. And A is invertible, so this means we can multiply both sides by A inverse. Right?
Yeah.
So V would be A inverse times all of this. me that all my brackets there. Okay. So what does that say?
Take C1 out, all C's outside, and it is C1 A minus A inverse TA plus C2 A inverse TA U2. You write that way, all of them,
Yeah.
and A inverse TAs are, called
Yep.
K1 is C1 A inverse, K2 is C2 A inverse. So you can find KI's that way, and we're gonna, you understand what I mean? If you call like K1 is A1 A inverse C1, K2 is A inverse C2. People love them that way, and then V is gonna be K1 TA U1 plus K2 TA U2, and so. Can you do that?
Right, but how do you know that that's like a scalar?
A inverse, you mean?
A inverse times C1. Remember, your k's in your equation have to be a scalar. I mean, basically what you're doing here is you're just running back to this. Because what would happen is the scalar would come out and A inverse times this. They actually kill each other. Because remember, TA means multiplication by A. So by taking A inverse, you're really just getting back here. Right? Remember when we write TA, it means just A times U1.
Yeah, but we have to prove that TA is, we have to write the linear combination of TAs, not the multiplication of them. So TA has to stay there, I think.
Right, but simplifying how you want to simplify wouldn't work. Because A would be some n by n matrix. You multiply that by C1, you don't get a K1. You see what I'm saying?
Yes, but I think we cannot change TA either to prove it.
Were there any other ideas? What do we want to show? Start there. What do you want to show?
C1 TA U1 plus C2 is V.
We want to show there exists C1 up to Cn such that this is true for any V in Rn. Right, so how do we know that's true?
Isn't the multiplier from Rn to Rn, so it has to be within it. Right?
Yeah, tell me how we can know this is true.
So then, like what we have on the left side for the first arrow, we could say the vector v, that t of v would equal t of the u1s to un, right?
Okay.
And so then that means that since TA is a multiplier from Rn to Rn, then that means TAV is in Rn, right?
You don't want to use T here. So you really do want to try to use the inverse, but you can't use it in this way. We're running short on time. Let's just actually do it. I'd probably do a contradiction. Assume not what would that hurt? Assume we can't find C's here. What does that break?
Independence.
Well, look at it this way. If I actually took A inverse of both sides of this equation, what would happen? This is an element in Rn, right? Because it's just a multiplication by a matrix, it's going to go to Rn. But what is this side? Because A inverse is going to kill this, right? When you multiply up, it's going to kill all the t's. So this side really comes down to what? Just C1 U1 plus da 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 Cn Un, right? But we know that the u's are a basis. So there's definitely a combination of C1 C through Cn that's going to give me the vector A inverse of V, right? But then if you assume that there were no such constants, then that couldn't happen. So this contradicts that, this contradicts that. U is a basis. Because assuming that we don't have coefficients that gets all the t's to get to any vector is the same as assuming that we can't find coefficients to get u's to be some other vector, which we know is impossible because it's a basis. Maybe move on. Running short on time, and I actually want to make sure we get through a fair share because our test is coming up soon. 4.5. Hopefully the questions are short. 22. What does that say?
Let S be a basis for an n-dimensional vector space V. Prove that if vector 1 to vector R for V.
So vector 1 to VR. Okay.
Form a linear independent set of vectors and V1 in the coordinate vectors V1 set S.
So this is in V,
Yes.
and they're linearly independent. Then the coordinate vectors do what?
Form a linear independent set and R.
That's actually pretty long. Probably the quickest way to do this one is to again talk about transformations, I guess, which I know we haven't spoken a lot about, but the book kind of jumped around and touched on it. There's a brute force way using what we've done so far. Maybe I'll mention that, but I just want to get this over with. So. So basically here, I have my V1, V2s, V3s, all these guys over here living peacefully. And here I have a subset of Rn. Call it, I don't know what to call it. Call it A subset of Rn. And what I'm going to do is I'm going to take a function that takes each vector to its coordinate vector. This function f. In fact, we kind of know how this function works, even though I never expressly called it like a function. But we know that for now, we can think of this as multiplication by a matrix. Right, we saw that setting finding the coordinate vectors. We just set up this matrix equation we found, and we can find it. So basically there's a linear transformation, some sort of function that I can apply to each vector to get its coordinate vector, right? So you think of it that way. So I can take a vector, and we can even sort of think of this as a change of basis. So with 4.6, you can kind of see this even more. But you can multiply this guy by a matrix to get a vector in terms of Rn. And so what we want to say here is the following. Assume so since U is a basis, spans V. U is linearly independent. So we're going to use this to our advantage here. So basically we know that we only need to show linear independence, right? Mm-hmm. Okay. So since U is linearly independent, we know that C1 U1 plus C2 U2 Cn Un equals 0 means C1 C2 all the way to Cn equals 0. We're going to apply f to both sides. So this means that f of this guy equals f of the 0 vector. This means that C1 times f of these should be V's. I think I'm calling them V's. And f multiplied by a matrix of the 0 vector gives us 0. So here we have, this is C1 V1S. Cn VRS. These are R's. So in fact, we can use the same coefficients to prove that these guys are independent. converse just means going the opposite way. Call this equation 1 for writing. So a non-trivial solution exists. Which implies non-trivial solution exists. Call this equation 2. Right, so I sort of went directly for one way and then I used the contrapositive for the converse. So assuming it's linearly independent, it makes these guys linearly independent, pretty much using this exactly the same coefficients. If I assume it's dependent, then again, using the same coefficients, I can prove that the other one is dependent. So there's linearly independent or dependent, the coordinates will be linearly independent or dependent. We'll talk about linear transformations in details, I think, in 4.9 and 10. So you'll understand that solution more as you move on. But for now, we're going to finish up 4.6 to pass the homeworks up to the front, and then we'll move on. So we kind of stopped in the middle of an example in 4.6 last time. Let's actually finish that example up and talk about some theorems we did. Last time, we had an example. We knew beforehand that B, in terms of the basis S, was -1, 1, 0. We know that B, in terms of the basis B, was what? 2, 1, -1?
Yes.
Right. And it turns out that we computed a matrix. Basically, we wanted to transform BS into BB. We computed the matrix. What we did was we took the basis for S. So what did I call the basis for S? Just S1, S2, S3. S1, B, S2, B, S3, B. So this, for example, this is the basis vector S1 or S written relative to B. Right, so we did that whole linear combinations thing and we set up a matrix equation we saw for that guy. We actually did that. I won't repeat it because we did it. You can look back to see what we did. And I believe that matrix looked like this. It was minus 3 over 2, minus 1 over 2, 5 over 2. Right, which was pretty much the coordinate vector for the S1 vector in terms of B. And then we moved on. This was a half, this was a half, this was 3 over 2, this was 1, this was 0, this was minus 1. We saw that if I took this matrix, minus 3 over 2, minus 1 over 2, 5 over 2, 1 over 2, 1 over 2, 3 over 2, 1, 0, minus 1. If I took that guy and I multiplied it by minus 1, 1, 0, the result was actually the guy that we expected to get in B. And that was very interesting. Okay, so now we're caught up to where we were last time. Okay, so I had a random vector V in R3, I think was the vector 1, 2, 3, right? S was a given basis, B was a given basis, and then I found the coefficients of the coordinate vectors for that vector V in terms of S. That was the result. We did it for B. That was the result. Now I wanted to sort of cut out the middleman. Could we jump between the bases B and S without first going through Rn, or R3? And the idea was we can. All we did was to go from S to B, I just look at the basis vectors of S, which were the three guys, S1, S2, S3. If I change those guys to be relative to B, then I can take that matrix that results, multiply any one in the space in terms of S, and I will get a vector in terms of B. And basically the upshot is this was not a coincidence. Turns out this was very calculated. The idea is the following. Write vectors into the space relative to a new basis. You simply need to transform the old basis vectors in terms of the new basis. Matrix that results from using these new vectors as columns is called a transition matrix. Right? Because we transition from one basis to another. So it's called a transition matrix notation. Something like this, P, and so in this case we're going from S to B. You'd literally write down here subscript S arrow B. This is the transition matrix. And basis S to basis B. In other words, if I take this matrix and I multiply by any vector that's in terms of S, I will actually get its corresponding vector relative to B. Right? So this is a matrix that goes from S to B. If I form that matrix, which basically comes from taking the basis vectors of S, finding their coordinate vectors relative to B, throwing them in a matrix in the columns, then I can take any vector in S, multiply by this guy, and I would get the corresponding guy in B. So I can literally transition from any basis to any other basis in theory by finding this guy. So let's write down our solution to the change of basis problem. That is the problem of changing one vector in terms of one basis into another vector into its corresponding vector in terms of another basis. So let B and B prime be different bases for a vector space. Let B be in B. And BSB coordinate vector. D prime relative to B prime respectively. Then give B to B prime times BB would give us B of B prime, and P of B prime to B times BB prime will give us BB, where Okay, so the idea is, if I want to go from B to B prime, I would change all the basis vectors in B to be relative to B prime. So I'm literally going to go B1 relative to B prime, B2 relative to B prime, right up to Bn relative to B prime. And if I want to go from B prime to B, then I'm going to change all the guys that were in B prime, and I'm going to write them relative to B. These are all vectors here. And we did an example of doing this, and so you might be wondering, is there an easier way to do it? Turns out there is. Systematic way to find PB to B prime or P B prime to B is the following. One. Set up this matrix. I actually wrote this out for our current example. So I'll show you how to get to the one that we found earlier. So here, old basis vectors, I mean set of basis vectors as columns. Right? So you put all the old ones over here, all the new ones over here. So your old basis that you want, you throw them all in this matrix here. The one that you want to transition to, you throw them here. 2. Bind the reducer or echelon form. Turns out the result will be, on this side you'll end up with IN. You'll end up with an identity matrix. And on this side, you find the transition from the old basis to the new basis. Example. In our previous example, I had B was the vectors 1, 0, 1, 0, 2, 1, 1, 0, 0. This was another basis for R3. It was 1 minus 1 minus 2, 2, 1, 1, 0, 0, 1. So if we had set up this guy, 1, 0, 1, 0, 2, 1, 1, 0, 0, augmented with 1 minus 1 minus 2, 2, 1, 1, 0, 0, 1. If I found the reducer echelon form of that, the result would have been this 1, 0, 0, 0, 1, 0, 0, 0, 1. And this guy would have been the guy we found before, minus 3 over 2, minus 1 half, 5 over 2, 1 half, 1 half, 3 over 2, 1, 0, minus 1. Which would have implied the transition matrix from S to B would be that guy. So this is literally changing each basis vector all at once. It's crazy, some remarks here. Things don't always work out this nicely. I just want to point out that this is working out because we're using the same vector space. Which means the matrix formed by the basis vectors is actually going to be a square matrix. Since the bases are linearly independent, the reducer echelon form is the identity. And they are invertible. And in fact, if I take the transition matrix from S to B, it's actually going to be the inverse of the transition matrix going the other way. So if you know one, you could also find its inverse to find the other guy. This is when you're going from this, you're jumping between the same vector space. You're just using different basis vectors for the same vector space. This gives you a square matrix, matrices, and all this thing. This works out very nicely for that. If you're going between a vector space here and a completely new vector space with different basis vectors, you don't get a square matrix, and then things get kind of, you have to sort of do row reduction all the time, and you don't really have this nice theorem. So it went kind of fast today. Any questions? Because I'm really piggybacking on all the work we did in the last class, so I know there's a lot missing here if you didn't read over your notes. But the idea is this: the basis vectors are really important. Those are the guys that we use to set up our coordinate system, right? Which tells us how to locate things, right? So sometimes they get outdated for some reason. We need to switch to a new way of locating things, switch to a new kind of coordinate system, right? So why the change of base is important is it allows us to do that, right? And whenever we're changing between, we're using the same vector space, things work out nicely because we have square matrices and linear independence gives us that everything's invertible. And so we can sort of use this row reduction method that we had for invertible matrices to be a shortcut. Basically, what's an example of what's going on here, where did we stop? So I know there's a lot of computation, and you might get lost into what's the point of all of this. So let me give you a small example before moving on. Computer graphics. You're programming a computer, trying to talk to a machine and get it to recognize certain shapes, right? You know, visual learning from a computer. So you want to tell your computer, okay, the goal is to hunt down ellipses, right? You tell your computer, an ellipse is something that looks like this, right? How do you actually tell a computer what that is, right? You might think of, okay, I can tell it the equation, right? I can say, okay, if you find the relationship between all the points and it's something like this guy, that's an ellipse, right? So then your computer is going around hunting down everything that follows this equation. Then it comes up to something that looks like this, though. Now, a human would recognize, hey, that's an ellipse. Would the computer recognize it, though? It turns out that that would not follow this equation, right? At least not in terms of the basis vectors I and j, right? So the idea is you have to program the computer to be able to change bases, right? If if I use I and j as my basis vectors, that's the equation, no problem, it can recognize it. But then if it's going around, you have to be able to tell it, okay, finding major and minor axes and then switching your basis vectors to two other guys, then find the equation in terms of the new basis, then you can recognize something as an ellipse. So no matter what orientation the ellipse has, right, your computer is going to be able to recognize it. And it's only going to be able to recognize it because it knows how to change bases. And how are you going to tell it to change bases? Well, this way. Right? So you're basically going to tell your computer, you're telling your computer how to tilt its head, basically. Right? Something doesn't have to look just like this. It can be skewed. Right? How does it recognize that? Right? And of course, later on, we're going to learn how to tell, well, what if it's stretched or shrunken or compressed or something like that. You need to be able to recognize it. Right? So that's sort of an idea. Somehow the way something looks, even though we know how it is in one frame of reference, right, in terms of one basis, things can change, right, depending on whatever reason, right? But so you need to know how to change things as well to be able to recognize something as you had before. And the idea behind that is to just change the basis, change how you look at the world, change how you locate things, and you can recognize something for what it actually is, right? So similar to how last time I said, you know, really if you're in like polar coordinates, it's rectangles that become circles, right? So if your computer wants to switch to like polar coordinates and it's looking for circles, it's not going to really look for circles, it should look for rectangles because it's looking according to a different basis vector. So that's sort of the idea. And the really nice thing is, once I know a set of bases for one way of looking at the world, if I want to change that entire world, I only have to change the basis vectors themselves, right? I don't need to go through and figure out what to do with every vector. If I figure out what to do with the basis vectors, I know what to do with everyone, because everyone else can be written in terms of the basis vectors, right? So all I have to do is to figure out how to transition from one way of looking at the world to another way, figure out how the bases will change, right? Once I know how the bases will change, I know how everyone will change, right? So that's another reason that makes bases really important. It's not just a matter of locating things, but we can literally affect everything by affecting them. Sort of like how if you want to get the army to do something, you don't have to command every single soldier, you command a few generals. The generals will take care of everything else. Right? So just know that that's sort of the idea behind everything. And if we're changing vector spaces altogether, your matrices won't be square, your dimensions won't line up, and you just do regular row reduction. But in the case where you're just doing two different bases for the same vector space, you get square matrices, your transition matrices all end up invertible because of the property of bases being linearly independent and all that. So it's really nice. We're going to talk about things like row space, column space, and null space. For now, we probably only have time to talk about their definitions, but we will come back to them. I can probably also tell you how to find it. By the end of this section, or actually I think it's the next section, we're going to have a theorem that really connects all these two and tell you why we even care about these spaces. These guys are some of what we call the fundamental spaces. So I'm defining what's called the row space of A, what's called the column space of A, and what's called the null space of A. And those are their notations. Row in brackets A, row column A, null A. Okay. This is this should be Fm. It's not always going to be the same. And this should be I want to tell you where these guys live. This is actually Fn. Well, we use row reduction to compute them, but I don't think we have time to do that. We'll pick up here next time. 4.6 homework is due on Wednesday.
I can see you're paying attention.